Well, welcome back, folks. We are doing the last class, the last night class of essentially the last day on campus, last normal day. So I appreciate you all making it here. That's kind of tough to do sometimes. I remember not going to the last class before break very often. But next class, even though the campus is closed and it is a week off, still I'm available with email, but there won't be any office hours. So feel free to email or text, and I'm happy to get back to you. But before we start today, any questions on the assignment number 7 that's due? Hang on, is that due today? No, we don't have an assignment that's due. Sorry for anyone that had a heart attack. Any questions on the coming up assignment that's due on March 28th after the break? That's probably the better question. Okay, so what we've been doing so far is accruing lots and lots of tests. The last test that we looked at was the comparison test. We need the comparison test because our series so far, before it's section 11.4, came out to a trichotomy where it was either a p-series, a geometric series, or something else that we had to tackle with the integral test, or possibly the test for divergence. Really, that's not enough tools to work with things like, if we take something like the divergent harmonic series and make it go from n equals 1 to infinity, say maybe n plus 3 divided by, how about n squared minus 1, this is in fact very similar to the harmonic series. And if we compare it in the right way to the harmonic series, then we can test this for convergence or divergence, never ever having to use the integral test. And there'll be plenty of cases where the integral test wouldn't apply at all. So this is the purpose of accruing yet 2 more tests. And once we're done with today's lecture, this would be the summary of the tests so far. What's kind of interesting about these tests are now that we have a comparison test, we take a series, a sub n, that we want to determine whether it converges or diverges, but we do that by making a comparison to a different series, b sub n. What now happens to this is we have to test this one for convergence divergence, which means we might use the test for divergence, the p-series test, or the integral test. So all of our tests so far can interact from the test for divergence to the comparison test with the 2 limit comparison tests. And that starts to become a pattern that we see quite often. Our tests start to become things that are used together. So let's start with the ordinary comparison test, and we'll go off to the limit comparison test next. Any questions before we start? Okay, so a typical problem in this section, we'll state simply test the series for convergence or divergence. But there's a lot of particular things that are implicit with those instructions. One of the things are that we'll go through all of the necessary steps of the chosen test. So say, for example, we do the integral test. We have to assert the function is actually continuous, positive, and decreasing. And we also have to do the definite integral. Then we have to state the overall conclusion, whether the series converged or diverged, and name the test that was actually used. So those are the 3 bullet points that we'd want to do for each one of these problems. And let's write out first, for our first problem, we have the series as k goes from 1 to infinity, summation k sine squared k divided by 1 plus k cubed. So that's the series we'd like to test for convergence or divergence. K is a little bit weird. If you wrote it with n, really n is a dummy variable to index the formula for the nth term of the series, but it's just as well could be k, j, or any symbol that you'd like. Another thing to keep in mind is if we're going to use the comparison tests or the integral test, we have to have sequences with positive terms. So having a sine function in there is a bit concerning, but because we're squaring sine, we're actually okay. The result of sine squared k is never going to be negative. So we're in good shape there. Next thing we want to do is compare it to something. So what we need to do is come up with the series b sub n. First and foremost, do we suspect that this converges or diverges by looking at it?
Guess converge.
I guess converge as well, mainly because k over k cubed, the power 3 is overwhelming, so I would say possibly the terms are getting smaller and smaller fast enough so that we have convergence. If that's the case, we're going to try to work the first part of the comparison test. And our job is to work out how to take a sub n and estimate it so that's less than or equal to some b sub n. So let's start. What could be helpful when you copy these problems onto either the chalkboard or your homework pad is name this so that when we use it in a theorem, we know what we're referring to when we say a sub n and b sub n. That can be very, very helpful. So I'll start by saying that this is going to be a sub k, rather, since k is playing the role of n. So now we want to take a look at a sub k, which is k sine squared of k, divided by 1 plus k cubed. Because we determined we think it converges, we're estimating in this direction. We're going to try to make it smaller than or equal to something else. And the first thing I'd probably want to work on is maybe the sine squared k. There's a standard estimate that we can make to this that is pretty common. And we start off by saying, first, sine of k is always less than or equal to 1 and bigger than or equal to negative 1. In other words, the amplitude of the sine wave can never increase over exceed 1 or be below negative 1. So that tells us, if we're dealing with sine squared instead, squaring both sides of this inequality takes all the negative values and makes them 0 or larger. So this would, from here to the next step, imply 0 is strictly less than or equal to sine squared k, which is less than 1. So that's a typical estimate that we could always make if we're dealing with trigonometric functions. If we have something squared, now this portion is less than or equal to 1, but bigger than or equal to 0. So we can immediately say that this is k times 1 divided by 1 plus k cubed. Does that make sense with that estimate so far? Okay, so the logic was we have less than or equal to on this step because sine squared k is always less than 1. Well, we should say less than or equal to 1. That is just for safety. Possibly sine squared k never actually hits 1, because that would have to be pi over 2. But next, we have to keep on estimating because we want to compare it to some series that we can test for convergence and divergence. And I cannot cancel k just yet. So this, if I put a summation symbol on it, is not a known series that I could work with. I mean, possibly we could be very clever with the integral test, but our goal is to avoid having to do that. So we make another estimate. This will be less than or equal to, I can't really do much with the numerator, so I'm just going to call it k. We don't want to estimate too abrasively, or else things can go awry. So we're going to work with 1 plus k cubed. 1 plus k cubed is definitely bigger than k cubed. So that's a nice inequality that we always have. And if we take the reciprocal of both sides, then 1 over k cubed would be less than 1 over 1 plus k cubed. So from this line, we would have this kind of estimate. And that tells us that 1 over k divided by 1 over, k divided by 1 plus k cubed should be less than, or hang on, this could be a problem. Uh-oh. I want to say it's less than or equal to k cubed. No, that seems right. Does that seem right to folks so far? Getting tripped up on the directionality.
The denominator is larger, so it's less.
Yeah, so I have a bigger denominator. I have a smaller denominator here, so this is going to be smaller, making this bigger. Here I have a bigger denominator, so this is going to be less. But what went wrong on this? Oh, I should change too much at once. I should really go like this. 1 over k cubed, and 1 over 1 plus k cubed like that. Oops, that should have been the correct direction. So if you take the reciprocal of both sides, don't also switch the position of k cubed, or that would not be correct. Does that look better to folks so far? Okay, so to get this kind of estimate, you could divide both sides by k cubed, divide both sides by 1 plus k cubed, and you'd also have to change the direction to make it look like this, and that would be the result. But that takes us to k divided by k cubed, which we could reduce to 1 over k squared, and this is what we would like to think of as the b sub k in this test right here. So you need to look at the series whose nth term is b sub k, or kth term is b sub k, and test it for convergence or divergence. But this is the main work, showing that this estimate holds. Any questions about making the estimate of a sub k less than or equal to b sub k?
When you take the reciprocal, isn't it less than or greater than, less than or equal to, sorry?
On this one right here?
On the sign flip, yeah, on the sign flip.
Oh, one from here to here?
From the first one you pointed out to the one under it, so 1 plus k cubed,
Yeah,
no, down.
here to here. Oh, sorry, right here.
Yes.
Gotcha.
When you take the reciprocal, doesn't
Yeah.
the greater than change to less than or equal to instead of just less than?
It just depends. If it was a greater than or equals to here, it should be less than or equals to over here. But if it's strictly greater than, it ought to be strictly greater than still on this one right here.
Okay.
And the reason is, if we work this one out, we have 1 plus k cubed, strictly greater than k cubed, and k itself is starting at 1, so we're never having to deal with dividing by a negative number or dividing by 0. The steps that we could take is divide both sides by k cubed, and at the same time divide both sides by 1 plus k cubed. So it would look about like that if we did that division. Then 1 plus k cubed is always positive itself, and it can never be 0. So we can do a cancellation that goes like this and this. So we get 1 over k cubed is greater than 1 over 1 plus k cubed. But this is just the same statement with the directionality reversed. So all I did is flip the order that I wrote the inequality. Does that make sense with that?
Yeah.
I felt like I should probably have been working that out from the start. That's very tricky to me. The directionality on the inequalities, to me, is the worst part about this specific comparison test. What are the questions so far about it? And another really bad thing about this comparison test is notice that if we had, say, a -1 here, a -1 here, and I went to this, that means the direction would have gone that way because I've increased it rather than decreased it. And that tells me if I use a greater than, I'm really in this land right here, but my b sub n is not going to work out because it would have had to diverge. So if we make a tiny sign change, the whole thing is ruined and the comparison test no longer works. But that's the purpose of the limit comparison test. If the comparison test doesn't quite work because of a sign of something, we can still get around to doing something else. What other questions or comments with that one so far? Okay, so the next step is we've verified that we have an estimate on the nth term of the sequence, kth term. K is really throwing me off. So we need to take a look at the series whose kth term b sub n and determine if it converges or diverges. So this is going to be compared to the summation as k goes from 1 to infinity of b sub k, and we found that to be the nth term, 1 over k squared. So would this converge or diverge? Yeah, we have 1 over k squared. We're really now thinking about a p-series. And in the p-series test, we have p equals 2, which is bigger than 1, and that's our condition for convergence. So we can say that this is a convergent. So we need the conclusion, and it's a p-series. So this names the test we're going to use. And the work is the power p is equal to 2, which is greater than 1. So the p-series are nice because when they come out in the comparison test, there really isn't much to do. If I had to use the integral test in conjunction with the comparison test, however, that would be a really terrible problem. So a good thing there's really not too many of those. Any questions to this step so far? Okay, so the logic of this comparison test is this series, a sub k, is always going to be less than or equal to this series, b sub k, when we look at the partial sums, just because the terms themselves are always less than or equal to b sub k. Since b sub k converges, we can say this total sum, which is always bigger than 0 and less than a convergent series, it has to converge as well. So our conclusion is, the overall conclusion, we really didn't care that much about b sub k. We just used it to determine if a sub k converges. So the conclusion is that the series, as k goes from 1 to infinity, of a sub k converges. And this is by the comparison test. So these are the kinds of steps that we would take whenever we use the comparison test itself. This was kind of a nasty one because we had to estimate sign at the same time as resolving what's going on in the denominator. But the common features are in the comparison test. You have to show some inequality like this, which produces the formula for b sub k. Then you have to test whether b sub k converges or diverges, then give the overall conclusion to the original series. There's a lot of steps going on in there. Any questions about them so far? So that's the good old comparison test. And like we mentioned, it does have issues. And one way we get around its issues is the same section is going to derive the following: the limit comparison test. A common question about the limit comparison test, once we see it in action, is, well, after we find that it's extremely effective, why do we even bother about the comparison test itself? And a short answer to that is, in certain situations, maybe that one was a bit much to work with, but in certain situations, the comparison test is highly effective. If we have to take a certain kind of limit involving sine squared k, for example, those limits do get complicated. So the comparison test is still a good test. Even though the limit comparison test seems like it's more effective, always keep this one at the ready in case we need it. The limit comparison test starts off as same as before. It says to let a sub n, as n goes from 1 to infinity, and b sub n, as n goes from 1 to infinity, be two sequences with positive terms. So we still have a bit of a dilemma. Our integral test, our comparison test, and the limit comparison test all say the nth term of the sequence must be positive. If that's violated, then there could be some index 5, where beyond 5 the series is, or the sequence is always positive. If that's the case, you can still use this test. But if the series involves things like cosine, so that's oscillating between positive and negative, then none of these tests will work. So part of our job in the next sections is to figure out how to get around these very stifling conditions that have to be held. So now, if we have that a sub n and b sub n are two sequences with positive terms, we can say the following. If we take a limit, because it's the limit comparison test, so if the limit as n goes to infinity of a sub n divided by b sub n comes out to some constant c, so it can't be a does not exist on this limit. It cannot be a limit that equals infinity. It has to be a real number c, and that real number c has to be bigger than 0. So if the limit comes out to exactly 0 itself, then just like the test for divergence, the whole test fails and no conclusion can be drawn. But if you form this ratio, a sub n divided by b sub n, take the limit, it's some positive value, then we have the following conclusion. Either both a sub n and b sub n, as n goes from 1 to infinity, converge, or they both diverge. And that's the statement of the test. So when we use this test, the a sub n as a series, oh, hang on, this was supposed to be a series. Let me try that again. Either both the series, as n goes from 1 to infinity, of a sub n, and the series, as n goes from 1 to infinity, of b sub n, both converge or both diverge. And when we apply this test, usually this is what we're trying to test for convergence or divergence. This is the thing we'll compare it to, and once we take that limit, if we determine this diverges, and we have a positive constant in the limit, then we'll say they both diverge as well. If this one converges, then if this limit is a positive constant, the original series that we're trying to test would also converge. So that's the statement of the entire test. Any questions about it? Okay, Also, one thing that's kind of interesting about this is you might see in some solutions that you don't necessarily have to divide in that order. If you did the limit of bn divided by a sub n, then you would still get a constant. It would be 1 over a constant, and it would still be positive if this limit is positive. So you can divide in whichever order that you would like, and it would be completely fine. But typically, I just take the a sub n coming from the series we're about to test and divide with that in the numerator. Let's try to apply this to a new situation. Any questions first before we look at new, more exciting series? Okay, so let's go off to something different. The last one that we tried to test was a very good one for the ordinary comparison test, because if we're dealing with trigonometric functions with limits at the same time, it's just not a whole lot of fun. So we'll leave that one there. But the new series we're going to test, as n goes from 1 to infinity, of a sub n, back to the index n because k drives me insane. This one will be 2n plus 1 in the numerator, divided by 3n squared minus n plus 1. So that's what we'd like to test for convergence and divergence. And if we were going to use the original comparison test, this could take an extreme amount of ingenuity. Because the trouble is, if you take 2n plus 1 over 3n squared minus n plus 1, and if we suspect that this, what would you say ought to happen? Converge or diverge? Any volunteers for a prediction?
Converge.
If we suspect it converges, then we need to estimate this way in using the original comparison test. And I could work that in the numerator. If I subtract 1 to make it 2n, this side is now smaller, 3n squared minus n plus 1. Now I want to make this bigger in order to get it less than. Well, to make it bigger, I could add n, but then I have the problem of 2n, 3n squared plus 1, and I can only make that bigger. I can't subtract 1, or else the estimate goes the wrong direction. So I'm essentially stuck here. I can't divide by n. We would have to do something else. Some more ingenious estimate might be found, but I'm not seeing it with this one. So the trick to determining which is the right test is if there is too much going on, and it looks like it's going to be a substantial problem in and of itself to try to make an estimate, like we attempted, then that's the case where you'd want to use the limit comparison test instead. So we're going to abandon this. It's just not working, and go to limit comparison. However, there's plenty of problems where this is a fast comparison to make, in which case this is probably the better test. But if we go to the limit comparison, this is what the steps will look like. We want to let b sub n be equal to something. We're not trying to estimate like we did in the previous problem and determine what b sub n should be. Instead, we're just going to analyze the form of the series and construct b sub n immediately. Because this is a rational function, what I would do is look to the highest power term in the numerator versus the highest power term in the denominator. If you took the constants 2 and 3, that would be okay, but it's not necessary. So I'll take the simplest sequence whose nth term would be n divided by n squared. So that's how I'm going to form the series I want to compare it to. That'll be the nth term, and this would reduce to 1 over n. So we'll compare the original series as n went from 1 to infinity, a sub n, to the new series as n goes from 1 to infinity of b sub n, which is the series as n goes from 1 to infinity of 1 over n. So what's the conclusion for this series, for b sub n?
Diverges.
Yeah, so this one we can just say immediately diverges. You don't even need to name a test. This is the divergent harmonic series. And it finds its way into lots and lots of problems. So that's another reason that we liked to name it. But if you did use a test, you could say it's a p-series. The p in the p-series would be equal to 1, and that's specifically the situation where we get something that's divergent. So that means we're now starting to suspect a sub n probably diverges as well, because that's the conclusion of the limit comparison test. If we form this limit, and if we get something other than 0, some positive real number, then we must conclude that the original series, a sub n, is also divergent. And so that's the motions of going through the limit comparison test. What are your questions so far to this step? Okay, so now let's go off and conclude the steps for using the limit comparison test. Whether we decide it is divergent or convergent, the next steps is always the same. We take the limit as n goes to infinity of a sub n divided by b sub n. And your conclusion would be the same if you took the reciprocal here, but this is the usual thing to do. Then this is the limit as n goes to infinity of, and here's where all this kind of stuff is starting to help out. I mean, this is really tedious to constantly rename the nth term of the sequence, rename the series a bunch of times, but it's handy if you're going to cite a formula that refers to a sub n and b sub n all over the place. It just helps us visualize what is really going where. So when we take a look at this limit, a sub n is referring to this as the nth term. So we'll take 2n plus 1, divide by 3n squared, minus n plus 1. Then we're dividing by b sub n, which is this, so we can multiply by the reciprocal, n over 1, to skip past that division. So that would be the limit that we must take. Any questions so far to that step? Okay, this reduces us all the way back to section 11.1. At this stage, we're just trying to determine the limit of a particular series, the ratio of a sub n divided by b sub n, and if we simplify this first algebraically, this is the limit as n goes to infinity of 2n squared plus n divided by 3n squared minus n plus 1. Then we mentioned there is a shortcut to doing this as a limit. Anyone see what the limit should evaluate to immediately? I heard 2/3? Yeah, this should be exactly 2/3. Reason being, this is a rational function. It's a ratio of polynomial over polynomial where the highest terms in numerator denominator match. If that's the case, this function has a horizontal asymptote at 2/3, but that's the meaning of limit as n goes to infinity. So you can, just by analyzing and determining what the horizontal asymptote is, the limit immediately. And that's always a fair step to take. If you wanted to work it out algebraically step by step, we've mentioned the trick is take n squared and divide numerator denominator, all the terms by n squared, and then you can take the limit. Then 2/3 would pop out. Any questions with that limit so far?
So I'm kind of confused.
Yeah.
How do you reciprocate the n, 1 over n?
Mhm.
Like, how do you do that? Like,
Oh, this right here?
yeah, I'm
when I
just
look-
confused, like, where, yeah.
I gotcha. So a sub n divided by b sub n would have really looked like this. 2n plus 1 divided by 3n squared minus n plus 1. Then that would be divided by 1 over n, like that.
Oh, okay, got you.
Yeah, so all I did was flip that around and made it be that. Just for the sake of saving chalk, because that's lots of copying. Other questions so far? Okay, so the work of using the limit comparison test is you have to produce b sub n, or the series b sub n right here. We can do that by analyzing the form of the original series and take the dominant terms from numerator denominator, if there's a numerator denominator, and go from there. The next thing is we evaluate the limit. Our limit came out to 2/3 for the c, and the important thing is that that is not 0. It's bigger than 0. So we're ready to state the conclusion. Either both series converge or they both diverge. That's where the work over there, saying we had the divergent harmonic series, is helpful. Since this was divergent and the limit came out to something positive, we can now say the original series converges. So this is our conclusion, finally. After a good amount of work, we say that the summation as n goes from 1 to infinity of a sub n converges by limit comparison test. So it's a pretty nice test because it sidesteps this kind of algebraic work, which can be substantial, or that kind of algebraic work, making the estimates. Any questions so far about the test? Should we try a couple more, just for the sake of practice? Okay, let's go to a couple more types of series. So let's maybe see if we can fit it over here. So this next one is going to be the summation as n goes from 1 to infinity of 2n squared plus n divided by the square root of 4n to the power 7 plus 3. Okay, so if you analyze the form of the nth term of this new series, once again, the comparison test looks like it's probably not going to work. Reason being is we have to make estimates that look like this, and it can possibly work, but lots of ingenuity could be required. To get these kinds of estimates to work out, the hope is signs are opposite, because I can make something smaller by subtracting n, make something bigger by adding 3. So this could possibly be a good limit comparison situation, but if the signs are both the same, then that original comparison test is probably not a great idea. I would instead go to the limit comparison test. So that means we have to produce the nth term of the series we're going to compare it to. So that's where the work starts. Once again, we go to the numerator. The dominant term in the numerator would be 2n squared, and it suffices to just take n squared. The denominator is new this time. It's not really a rational function because we have a square root to the denominator. There's 2 possible horizontal asymptotes now. But if we look at the most important term right here, what power would you give n to n, base n in the denominator?
But as 7 divided by 2.
Yeah, exactly. Because if we looked at just something like this, root of n7, this would really be n7 divided by 2. So that's the power of the term that's most important in the denominator. Does that make sense so far? Okay, so we take b sub n, we form it by taking n squared to the top, n power 7 from the bottom, but because it's a square root, we'll divide it by 2. So that's our b sub n. So we could say now that if we simplify this, and we definitely should, because we're going to have to test a series for convergence divergence again, we'll simplify by saying n squared is really n to the power 4 halves, divided by n to the power 7 halves. Then altogether, if we divide from here to here, we would have n to the power of 3 halves. In other words, we can just subtract the exponents. Does that make sense so far? Okay, so with some exponent laws work, we get to this, and now we can say, then, the series, as n goes from 1 to infinity, of b sub n, which is the series as n goes from 1 to infinity, of 1 over n to the power 3 halves, is a p-series. So that essentially names the test, the p-series test. If you just call it a p-series, then that qualifies. The exponent p is 3 halves, which is greater than 1. So b sub n, if we want to refer to the series briefly, this would be a decent shortcut. That's pretty common. If you suppress where the index goes to, then it'll be summed from 1 to infinity, and this converges. So this time we have something convergent. Any questions so far? Okay, so now we have to take the limit of a sub n. I forgot to name this as a sub n. Let's just do it right away. So we'll always have essentially a variable to refer to that entire thing. We need to form the limit of a sub n divided by this b sub n, which means we probably need some more space. So let's take away the older test and form the limit as n goes off to infinity of a sub n divided by b sub n. Or b sub n divided by a sub n is going to give you the same conclusion. So this will turn into the limit as n goes to infinity. First, I'm just going to copy what a sub n is. It's 2n squared plus n divided by the root of 4n to the power 7 plus 3. Then we're dividing by b sub n, which means we'll take this and multiply by its reciprocal, just to save a step. That would give us n to the power of 3 halves divided by 1. Does that make sense to that step so far? Okay, the next work would be, we should simplify this as much as possible before we actually take the limit. So we'll take n to the power 3 halves and distribute it in. This will be the limit as n goes to infinity of 2 n squared times n to the power 3 halves. I think we've done that before. No, we have not. That's going to be, let's see, n squared can be thought of as power 4 halves to get the n squared. Multiplied by n to the 3 halves is n to the 4 sevenths. Then here to here, we can put the power of n, which is 1. We express it as 2 halves. Then we multiply by 3 halves. The exponent will add to 5 halves. Any questions with that exponent loss to that step? Okay, then it's just 1 times the root. So down below is the root of 4 n to the power 7 plus 3. And ordinarily, this might be a pretty nasty limit because functions that look like this have 2 horizontal asymptotes, which is unusual, whereas a function that looks like this, a true rational function, has exactly 1. So in this case, first let's make a prediction. What would you say the limit should be if you had to guess? Suppose you had 5 seconds left on an exam. What's the limit?
1/2?
Yeah, exactly. We got it. So we'll turn in the exam and be good. So the way we can do that is the dominant term here is, or hang on, this would be 7 halves. Sorry, that is some really, really bad fraction arithmetic. That should have been 7 halves. So now we can make a better prediction. We take the coefficient of 2 that had power 7 halves, and because this is a square root, this is effectively, if the 3 was gone, n to the power of 7 halves as well. So we can take the coefficient 4 and do the root of 4 down below. This is taking a shortcut, and it's a dangerous shortcut, because if we go to negative infinity, which we'll never do in chapter 11, but if you did do that, it'd be the opposite of this sign. So there is some algebra that is sometimes good to do. So this will be 2, the root of 4 is 2, which is 1. I'll leave it up to you folks. Should we work out that limit a little bit more carefully without shortcuts?
Yeah, I got a question about that.
Sure.
So like, wouldn't the 2n be the square root of 7? And so wouldn't it be the square root of 2 over the square root of 4
No.
on top?
This would, oh, up here. So the square root of, sorry, I got lost. What was the original
So
question?
wouldn't it be like the square root of 2 on top, on like the right? Because it's the 7 halves, right?
Right here, yes.
So it would be the square root of 2n to the 7th?
Well, the power 7 halves is not affecting the 2 itself.
Oh, okay.
Unless it looked like this. If it looked like this, that'd be absolutely right. We
Oh,
have the
okay.
root of 2 to the power 7, some huge, huge number.
Okay, that makes sense.
Other questions so far? Okay. Does that seem all right to folks to work out the limit carefully, just to be sure we're on the right track? Okay, so this is a shortcut. It's a huge shortcut, and it is appropriate if you feel comfortable with it. But let's work that out with a little bit more careful details. We want to form the limit as n goes to infinity of, let's take 2n to the power 7 halves. Then we'll take n to the power of 5 halves divided by the root of 4n to the power 7 plus, was that a 3? Yeah. So if we want to work out this limit very, very carefully, then the algebraic tricks that we will use is we always look to the denominator. The most dominating term in the denominator would be 4n to the power 7, which is under the root. So what we'll do then is multiply the entire thing by 1 over, we're not so concerned about the 4, it's more about the n power 7. We take n to the power 7, but because it's a square root, we really take 1 over n to the power 7 halves. We'll multiply that into the entire numerator, and we're multiplying by 1, so we have to do the same thing into the denominator. So that's what the steps would look like so far. So once we do that, this will become the limit as n goes to infinity. Across the numerator, when we distribute, n power 7 halves divided by n power 7 halves gives a cancellation of 2, plus n to the power 5 halves divided by n to the power of 7 halves. So that resolves the numerator. The denominator is a little bit more special because it uses more exponent laws. we could say, for example, we're trying to take 1 over the square root of n to the power 7. So that's our n to the power 7 halves, and we're multiplying it into a square root of 4n to the power 7 plus 3. So this is how we're trying to visualize it. But square roots with multiplications, critically, are pretty forgiving. For example, you could apply a formula that says the root of a times the root of b is the same as root of a times b. But that completely breaks down if there's a plus or minus between the a and the b, sadly. There's no good formula for that. So in this situation, we can say that this whole thing becomes 1 overall root of 4n to the power 7 plus 3 multiplied by 1 over n to the power 7. So the n to the power 7 creeps inside the square root in that way. Does that make sense, visualizing it that way? Okay, well that means once we do the cancellations, this root would become just a 4 from here to here, plus 3 divided by n to the power 7. So that's a pretty ugly spot of algebra. And the reason this is pretty a dangerous step to take is if we went to negative infinity, then this would be a negative number, and the algebra does not quite work out. We'd have to do something a little bit different. And it would get a second horizontal asymptote with a negative sign. But at this stage, we can say, if n is going to infinity, well, this overall would go to 0. Does that make sense why? So maybe write one extra step. We can say that this is the limit as n goes to infinity of 2 plus, we could divide power 5 halves of n into n power 7 halves to get n to the power of 2 halves, or just n in the denominator. So altogether, we're just dealing with the 1 over n. Down below, it's 4 plus 3 over n to the power 7. But now we're letting n run off to infinity, and when that happens, this term will converge to 0, and so will this term, even though it's inside the root. So the whole thing finally, and this is our shortcut, becomes 2 over root 4, which is 2 halves, or 1. So that's the algebraic steps you can take to do that limit. Any questions about them? Okay, so that's a substantial amount of algebraic steps. This is a big problem already, as aside from testing for convergence or divergence. So if you know you're going to positive infinity, that's very, very important. If you have a function of this form, going from here, analyzing the 2 and the 4 under the root, all the way to here as a shortcut, that is okay to take. That way you get to focus on the stuff that is maybe more important, learning the limit comparison test. But any questions so far with the limit? Okay, this problem was so long, let's recap of what we've done. We're testing this for convergence divergence. So we took n squared, n to the power 7 halves down below, and this is what we're going to compare it to. It turned into this, which is a convergent p-series. So now in the test, we take the limit of the ratio an divided by b sub n, and we got a limit of 1, which is bigger than 0. So this condition qualifies. Now we know that both series converge or they both diverge. But the thing we compared it to, b sub n, did converge, so we can conclude that the original series, as n goes from 1 to infinity, a sub n, also converges. And another thing that's horrible about this is we want to state the name of the test. Sometimes that's a lot of writing. But if you wrote LCT, the only thing that I would possibly think you meant is limit comparison test. So that's a decent shorthand if you want to just save a few seconds writing. Any questions with that kind of problem? So that's the limit comparison test, and these are the standard kind of problems that you'll see it in. There's plenty of situations where it just does not work. But if you have ratios like this, a rational function, or something close to a rational function, then that's almost a dead giveaway that probably the limit comparison test is the best thing to use. But what we want to do next is we're starting to deal with a lot of tests. And the number of tests is going to start to grow. When we come back from the break, we'll do the alternating series test, so we can have positive and negative terms. We'll do the test for absolute convergence, and then a couple more really, really fancy tests. But so far, I think it's a good time to pause and just try to see how these tests all work together. So let's go to a new problem somewhere. This is stolen from the book Calculus Early Transcendential Functions by Larson and Edwards, 5th edition. And it's a pretty clever problem to study all the tests that are on the table so far. So we have altogether 8 different series we want to test for convergence or divergence. And this is really kind of a special set of instructions. We want to use tests 1 through 7, where one of them is really the definition, at least once. So we don't want to use, for example, the limit comparison test more than twice, or else we wouldn't have used all the tests. So let's go down the line. I guess there's a couple ways you could do this. You could figure out which one converges by the definition, or we could just go down the line of each one of the series and work those out. I would probably start with series. Does that sound all right to folks? Okay, so we want to determine which one would converge or diverge and by what test. Really, the purpose of this exercise is to really just train our eye into analyzing what the form of the series is and what the appropriate test is. So as a first wave, let's just go through and just say what test we would pick. Then if we have more time, we'll try to actually run through all steps of the test. So first one with this, what would you say the appropriate test should be for this series? Cube root of n divided by n. Probably as an initial step, you could rewrite it as n to the power 1/3 divided by just n. And if you did that, you could also say the power of n on the denominator is 3/3. So a really helpful step in analyzing this series is take the nth term and start simplifying it. Sometimes that can tease out details that are not always easy to see on the first glance. So if we worked out this division, this would be 1 over n to the power of 2/3. It won't format the way I wanted to, but that's okay. So if it's 1 over n to the power 2/3, what kind of series would you say this must be?
P-series?
Yeah, here we're dealing with the p-series. So that would be this test right here. So it's a p-series, it in fact would converge, so this only takes a moment to write. So let's write this out. So this is a p-series. P is equal to 2/3, which is less than or equal to 1. Let me try to make that prettier. P is 2/3, which is less than or equal to 1. So the series diverges. So that's one down. Any questions with that one so far? Okay, so we're off to series 2 of 8. What kind of series would you say this looks like?
Geometric series.
Yeah, exactly. This time we have a value a here for playing the role of 7. Here we have something we would call the Kármán ratio, r. And critically, the only place the index ever appears as an exponent. So that means it's a geometric series. But first let me keep in mind we're trying to use these at least once. So I'll try to remember that one's now done. And we have a we have a geometric series over here. So that one's also off the list. So this is, and I'll save this work as well. So if you want to, if this is probably way too fast to actually take notes on, you can refer back to the Moodle website for what we produce on here. But we can say that this is a geometric series. R is equal to -1/7. So the absolute value of r is less than 1. So the series converges. And we could do a little bit more, but that was really a problem for the second exam. If a geometric series converges, this is one of those very rare cases where we can say exactly what it converges to. But if the instructions is just to test for divergence, convergence, you can stop at that stage. All right, questions to that step on this one? Okay, but just for the sake of completeness, what it would converge to is 7 divided by 1 minus the Kármán ratio, which is -1/7. And then we could just work that out algebraically for what it comes out to. So let's go off to the next one. 1 over 5n plus 1. What does that look most similar to? It's definitely not geometric. What's breaking the geometric series is that. If it was just 1 over 5n, then everyone would be happy. That's a geometric series. We can use one of the tests twice, but because it's 1 over 5n plus 1, it's not exactly a geometric series. So what sort of test would you folks say we ought to use?
Test for divergence.
Well, the trouble with tests for divergence is that if we took the limit as n goes to infinity on this one, let's write that out just for future reference. The limit as n goes to infinity of 1 over 5 to the power of n plus 1, it would come out to 0, sadly, because we would have a numerator that's constant and a denominator that's growing exponentially, plus 1. So the whole limit would be 0, but that means the test for divergence can't be applied, because this could now either converge or diverge. So we can say test for divergence cannot be used. But that's really good information too. That means we can now narrow it down to the next best test.
Comparison?
Yeah, I would like to do a comparison test on this one. What we could do on that one is say, if a sub n is equal to 1 over 5 to the power of n plus 1, then let's make this be 1 over 5 to the power of n. So look carefully now, I made the denominator smaller. That means this side should be bigger. Does that make sense so far? Then, if we let this be the b sub n, then the summation as n goes from 1 to infinity of b sub n will be the summation as n goes from 1 to infinity of 1 over 5 to the power of n. So that is the geometric series. It would be convergent. The common ratio is 1/5. That means the original series must converge by the comparison test. I mean, there's details that we would have to add to this, but since we're running short of time and we have 5 more to go, let's say the comparison test may be used. And this is a wonderful case to use a comparison test because the estimate is straightforward and determining if the thing we compare to converges or diverges is pretty rapid. So that would be the best test to use on this one, which means that one's gone. So let's get rid of that and go off to this one down below. 1 divided by n cubed minus 8. I've changed that to n is equal to 3 because if you start it as n equals 1, then when n equals 2, you would be dividing by 0. So we have to make a slight modification there. This one has a problem in that if we say a sub n is equal to 1 over n cubed minus 8, and we go to a fraction 1 over n cubed, what's the direction on the inequality? Is this less than or greater than?
Less than?
I think it's greater. Yeah, these always mess me up. So every time I always check carefully. And the way I would work this out is, this is the smaller thing. Would you folks agree? As far as denominators go. So if I make the denominator bigger, then 1 over that denominator is going to be a smaller quantity overall. So the direction should go this way. The right-hand side is smaller for a greater than sign. So that's interesting because if we want to use, say, the comparison test for convergence means we should be doing less than. This is what we would have to be using. However, instead, down below, we have something that we would compare to a thing that converges, the series with 1 over n cubed, and by direction is the wrong way. I have something bigger than a convergent series, which means this could either converge or diverge. It also tells us, this is still not wasted work, it's important work, I'd say. This shows that the comparison test cannot be used, sadly. Whereas it worked just fine here because of the plus 1. If we convert to minus with something that should converge, then the whole test is ruined. That's tragic. But what's our next best test after that?
Integral test we use a use of.
Possibly. Yeah, I think an integral test could work on this, but the u sub might be really, really clever because I'm not sure what the u would be. If we were to integrate, for example, 1 over x cubed minus 8 dx, it seems like a tough u sub. Not that it's impossible, but it could require, this is a horrible word, lots and lots of ingenuity to make it come out. So if we didn't do the integral test, and not saying it wouldn't work, what's the next best test? Yeah, exactly. Whenever the comparison test has failed, but we still feel like it should converge and we still feel like there's something we want to compare it to. For example, we would like to compare it to 1 over n cubed. Exactly, or essentially, this is our goal. That's the problem I want. It won't work with the comparison test, but the limit comparison test will absolutely work on this one. So instead, bold, because if the comparison test has failed, that would always be my next go-to. Try the limit comparison test. The limit comparison test may be used. So limit comparison test is now off the table. So let's go strike that through. We now have the definition of a convergent series, test for divergence, and the integral test. So we're starting to narrow these down. And one of the tests can be repeated. But first, if we look at this one, what feels like the best test amongst test for divergence, integral test, or the definition of convergence?
Same powers, so the limit comparison test.
It could actually be used,
I can,
but there's a faster test that we could use. This is very tricky, don't feel too
would
discouraged.
just be the test for divergence.
Test for divergence is the one that we could use on this. And like you were saying, if we look at that in the limit of not this series, but the nth term of the sequence, we would get a 2/3. So let's write this out. Limit as n goes to infinity of 2n divided by 3n minus 1. We know just by inspection that limit should be 2/3, which is not equal to 0. So if we go to the limit comparison test, that's down below, the limit comparison test says if the limit does not exist or if it's not 0, that's what happened to us, our limit is 2/3, not 0, then the series is divergent. Keep in mind there's just one conclusion to that test for divergence. So we can come up here and say the series diverges by the test for divergence. Any questions with that one? So the test for divergence is special because it did come from section 11.2. When we take our exam, we're trying to focus on 11.3 into 11.10, but the test for divergence is something kind of like integration by parts that does carry out throughout the entire chapter. So this is something that you should have always at the ready. And one thing you should also get in the habit of doing is if you can eyeball the nth term of the sequence and see that the limit cannot possibly be 0, then you'd want to use that test right away. I mean, it fails repeatedly. This is in the limit would be 0, this in the limit would be 0, and so would this. This also has a limit of 0, but before you even consider any test at all, eyeball that. The nth term, what's highlighted in the limit is 2/3, so immediately don't try anything else. The test for divergence is the fastest thing to do. Any questions about that? Okay, then we go off to some weird things. This one we've solved way back, which is a telescoping sum. So this is a telescoping sum. Makes it telescoping is the fact that we have two terms, two fractions in this case. They don't necessarily have to be fractions, but two fractions or two terms separated by a minus sign, it gives us a telescoping sum. When that's the case, we can write out the formula for S sub n, which is equal to a1 plus a2 plus all the way up to a sub n. And as soon as you get that formula, compute the limit as n goes to infinity of S sub n. If that limit exists, then this would converge by the definition of convergence of a series. So this is, really there's two rare cases. One rare case where we can get a formula for S sub n is telescoping sums. The other very rare case we can get a formula is the geometric series, and that's why we could give the total sum in both of these cases. So this one would be, this converges, we would have to show those details, but this would converge by the definition of convergence. So with about 7 minutes and some change, I'll leave it up to you folks. We could run through the steps on actually showing this, or go to the next two. Anyone for going to the next two? Okay, let's go to the next two. Overwhelmingly, we want to take a look at this one. But first, let's analyze the situation. We've done the test for, both of these so far, so we can strike these through. Oh, that's the wrong shortcut. Hang on. There we go. So all that's left is the integral test. Which one of these seems like the best case for integral test to you folks?
One on the left.
I would agree. What's great about the one on the left is if we made a u substitution, u is x squared plus 1, then du would involve an x. Or the value n up above is allowing an integral test to be not too bad. It is still pretty bad, but we can use the integral test on this thing. So this can be tested using the integral test. Possibly we could also use other things. We may be able to use a comparison test, for example, or a limit comparison test. But what we were trying to do in this problem is say which is the best one, essentially, for the integral test. And I would say it ought to be that, oh geez, it ought to be that one. So we've used all tests exactly once. That means we can do a repeat on this one of any single test. So if you look at 3 divided by n times n plus 3, well, the limit of that as the nth term would be 0, so test for divergence is out. It's not a p-series, yet it's similar to 1. I would say some kind of comparison test ought to be the best way to go on this one. So which test would you folks use? Comparison test or limit comparison test?
Comparison.
So I think the comparison test would work really well on this. We could estimate by making this go from n plus 3 to just n. If we did that, we'll have a nice estimate, and the comparison test should work. If something goes awry, for example, if the direction of the inequality just does not behave like what happened in this, then just default to the limit comparison test. So we'll test this using the original comparison test. So we have a good idea of what should go to what based on the form of the series. Again, this is pretty tricky, but it's some of the things that we have to start thinking about when the number of tests increase. Any questions so far with this problem? Okay, so with 4 minutes, we could try to determine what happens to each one of these last 3 that we didn't give very many details to. I think one that looks extra fun to do. Well, to be honest, in about 4 minutes, we may not make it in time. So it might be just because it's spring break coming. We all worked really hard. We've just analyzed 8 different series all at once. How about we do ourselves a favor and call it a day? Does that sound all right to folks? Okay, so we're ending a few minutes early, but we've gone over before, so I think our time balance is close to 0 anyways. If you have questions, you can still stick around. I'll be here. I'll be happy to help. And I'm going to intend to save this and upload it to Moodle. So if you'd like to refer to it later, it'll be available. But there'll also be the PDF version that is blank. So if you just want to start over scratch with what is essentially a worksheet for extra practice, see the PDF version here.